Let's take a look at the remaining problems in the 7.2 Achieve assignment, still talking about the integrals of trigonometric functions. For number 11 here, we have the integral of tangent to the fifth of 16x times secant to the fourth of 16x integrated with respect to x. So as soon as I saw this problem, and I'll go ahead and maximize this to look at it better here with you. So as soon as I saw this problem, what I did is I knew I was going to work with the tangent function, because what I'm wanting you to remember, anytime sine, cosine, tangent, or cotangent are to an odd power, it's going to be to your advantage to go ahead and break up all but one power of that function in terms of another. So what did I do? I said, well, tangent to the fifth is tangent to the fourth times tangent to the first. I'm going to put the tangent to the first of that angle at the very end. So the other, tangent squared quantity squared, I know tangent squared is equal to secant squared theta minus 1, in this case secant squared of the angle 16x minus 1. That's equal to tangent squared. So tangent to the fourth is that group squared, times the secant that I already had in there of 16x. I integrated all with respect to x. As soon as I do this, I know I would like to let u equal the secant of x, or sorry, secant of 16x in this problem. So when I take the derivative of secant, I would get 16 secant tangent. It's the derivative of the trig function, which is secant tangent, times the derivative of the angle, which is where we get our 16. Now, in order to take this derivative and use this substitution, I would need to see the 16 secant tangent dx in the problem. Well, clearly I have the tangent and I have multiple powers of the secant in there. So here's what I'm going to do. I'm going to say, well, I need to multiply the inside by 16. So you'll see I did that in red, or it almost looks like pink there. But if I multiply the inside by 16, I need to divide by 16 on the outside. That leads me to my next step. The integral is equal to 1/16. This group is going to become u squared minus 1 quantity squared. Do you understand where this u cubed came from? Please understand here, I had to take one power of this secant to go along with the tangent for this du here. In order to substitute in du, I had to have a factor of secant, tangent, 16, and dx. So all of this and one of the secants had to go to become du. Well, that left me three other powers of the secant of 16x there. So I just replaced that with u cubed. So now this is gorgeous, because I can say, well, I can FOIL out this group. U squared minus 1 times u squared minus 1 would be u to the fourth minus 2u squared plus 1. I do that and I distribute through a u cubed through every term. That's what gives me this. I just didn't want to take 2 steps to do that simple algebra. So I FOILed out that group, distributed u cubed to get to this polynomial in there. Now once I do that, I know I can just integrate by the power rule, add 1 to the exponent and divide by that new exponent. We get u to the 8th over 8. The next term would be minus 2u to the 6th over 6. I go ahead and reduce that down to u to the 6th over 3, and then plus u to the 4th over 4. Once you do that, you know that for the final answer, I'll go ahead and distribute the 1/16. In general, I think Achieve would prefer you to distribute. You don't always have to, but it's probably wise to in most cases. So I did that, and then my u to the 8th becomes secant to the 8th power of 16x. My u to the 6th, of course, secant to the 6th power of 16x. And secant to the 4th of 16x replaces the u to the 4th. Don't forget your constant of integration. Now for the next problem here, number 12, we have an even power of tangent times an even power of secant. Instantly, when you see that, you should say, oh, okay, I only really want to work with odd powers of sine, cosine, tangent, and cotangent. I'd rather not work with an even power of tangent. Remember, we do want to work with even powers of the secant function. So I'll say, that's what I'm going to attack. So that secant to the 4th, I know, is secant squared times secant squared. One of those secant squareds can be rewritten with its Pythagorean identity equality of 1 plus tangent squared x. All right, Now, if that's 1 plus tangent squared x, I know I'm going to let u equal the tangent of x. And then du is going to be secant squared x dx. Beautiful. All of that just becomes du in the next step. What did I do out front? I knew that this tangent to the 18th would distribute through that group. And when I turn it to u, it's just going to become u to the 18th plus u to the 20th. That's what I've done from here to here. Now, once we get to that point, you just integrate with the power rule and then back substitute back in your tangent in the place of u. So I get tangent to the 19th of x over 19 plus tangent to the 21st of the angle x over 21 plus your constant of integration. It's a pretty quick problem there. For the next one, again, you're supposed to remember you want to work with odd powers of sine, cosine, tangent, or cotangent. You only want to work with even powers of secant and cosecant. So as soon as I see this, I know I want to work with a cotangent to the 5th. So I do. I say it's cotangent squared squared times cotangent. Cotangent squared is equal to its Pythagorean identity of cosecant squared x minus 1. Now I'll go into my problem and say, well, all right, I'm going to call this cotangent to the 5th cosecant squared x minus 1 squared times the remaining factor of the cotangent, which I'm choosing to put at the end right next to the dx. I left my cosecant to the 9th in there alone for now. Now, when I do this Pythagorean identity substitution in the problem, I do that with the intent of, I know I'm going to let u equal the cosecant of x. If u is the cosecant, then the derivative of u is going to be, derivative of cosecant is negative cosecant cotangent, and that's the derivative with respect to x. Okay, so now I didn't see the negative inside of there. I multiplied the inside by -1, multiplied the outside by -1. When I do that, I now know that -1 times cosecant cotangent dx is all going to become du. But now keep in mind, this was cosecant to the 9th. Only one of the powers of that cosecant needs to go along with the cotangent in the dx to become du. Well, that's why you've got a u to the 8th left over there along with the du. So one power had to be going along with the substitution. All 8 of the other powers of cosecant still stay in the problem. So cosecant to the 8th becomes u to the 8th. I went ahead and squared out this and put it in terms of u. It would have been cosecant to the 4th minus 2 cosecant squared plus 1. That's written as u to the 4th minus 2u squared plus 1. Now we still have the negative out in front. At this point, you must do the algebra before you do the calculus. So multiply by the distributive property that u to the 8th through that trinomial. You get to this polynomial, and we're still integrating with respect to u. So then you say, okay, power rule tells me that the first term is going to be u to the 13th over 13. My second term is going to be minus 2u to the 11th over 11. And then that last term there, I'm sorry, I'm trying to make it a little clearer there. That's better. Is going to become u to the 9th over 9 plus your constant of integration. All right. Now, at that point, I can go in and say, once I have my final answer in terms of u, let's put it back into terms of x. Everywhere I see a u, I replace it with a cosecant of x. So I have negative cosecant cubed x over 13, negative cosecant to the 13th x over 13, I should say, plus 2. This u is to the 11th, so I have cosecant to the 11th of the angle x over 11 minus cosecant to the 9th x over 9 plus c. Now, keep in mind, I typed it in to achieve identically that way, and it was absolutely fine just doing those fractions like that. If you prefer to put the coefficients like -1/13 out in front of the cosecant to the 13th, that's fine too. So either format of the answer would be acceptable on these problems. Looking at another problem here for number 14, the original problem, the red is just how I went from the original to the next step. So the original problem was just the integral of t cosecant cubed to 5t squared dt. As soon as I saw I had an angle that was a fairly complicated angle, it's a quadratic inside of a trigonometric function, I knew I wanted to do a u substitution to get rid of it. So I set u equal to 5t squared. I know the derivative is going to be 10t with respect to t. I saw the factor of t on the inside. I didn't see the factor of 10. Well, all right, I multiply by 10 on the inside, divide by 10 on the outside. Now from this step to the next, that 10t dt all becomes du, okay? Now what's left over? Well, it's the cosine cubed of 5t squared. Well, that's going to be the cosine cubed of u, since u is 5t squared. Now, as soon as I get it down to an odd power of a cosine, I know instantly what I'm going to do. I'm going to break all but one power into the sine function. I know cosine cubed is cosine squared times cosine. Cosine squared is equivalent to 1 minus sine squared. So I have 1 minus sine squared times the cosine, still integrating with respect to u. So I'll choose another substitution, and now w is going to equal the sine of u. Well, then the derivative of w would be the derivative of the sine of u, which is cosine of u, with respect to u. Okay, I needed to see a cosine u du in there. I do. So I know that this substitution is extremely easy. It's just right straightforward. The cosine u du becomes dw. This group right here is going to become the group 1 minus w squared. At that point, I can integrate with just the power rule and say it's going to be 1/10 times the first term integrates to w to the first, second term integrates to w cubed over 3, plus our constant of integration. Now I've shown both steps in the back substitution. So w is equal to the sine of u, so this becomes the sine of u minus sine cubed u over 3. And then when I say, yeah, but u is equal to 5t squared. So then the next step, I have the sine of u becomes the sine of 5t squared minus the sine cubed of 5t squared over 3 plus your constant of integration. And I just left that answer in factored form when I did it on Achieve, and it liked it just fine. Typically, they want you to distribute out, but the factored answer here was perfectly fine. For the next one here, I want to look at 15. In 15, we have the integral of cosine squared sine of 5t times the cosine of 5t integrated with respect to t. Again, the red is what I did afterwards. This is your original problem. As soon as I saw that I had the sine of 5t as the angle inside of a cosine function, I knew that's going to have to be my initial substitution. I'll let u equal the sine of 5t because it's a function inside of a function, technically inside of another function. This is that'd be a 3-level chain there. Gorgeous. But I'll let u equal the innermost term, well, sine of 5t. Now, derivative of u be the derivative of sine, which is going to be cosine of that angle times the derivative of the angle with respect to t. I get 5 cosine 5t dt. So now I don't see the 5 as a factor on the inside, so I put it. I multiply by 5 on the inside, I divide by 5 on the outside. This is going to equal 1/5 the integral. This becomes cosine squared of the angle u, since u is the sine of 5t. And then everything else is du. Now, at this point, in order to do the integration for that, you can't integrate the second power of the cosine function. So I use a wonderful trig identity from Calc 1 that says the power reduction formula for the cosine squared is equal to 1/2 times 1 plus the cosine of 2 times the angle. Okay, so if it's cosine squared u is 1/2 times 1 plus the cosine of 2u, I can say, well, that 1/2, I'm just going to factor out front along with the 1/5. 1/5 times 1/2 is 1/10. Now I'll have cosine squared on the inside becomes 1 plus the cosine of twice the angle. I can now integrate that by saying, well, the integral of 1 with respect to u is just u. The integral of the cosine of that angle is going to be the sine of that angle divided by the derivative of that angle, which is where the 2 is coming in. Integral of cosine of 2u is the sine of 2u over 2 plus your constant of integration. Now, when I'm going in to try to think about my final answer here, I went ahead and said, well, this is going to be 1/10 u, which is 1/10 the sine of 5t. And then I would have 1/10 times 1/2 for 1/20th, the sine of 2u, which is going to be the sine of 2 times u, which is 2 sine of 5t plus the constant of integration. Now, I actually tried putting that as an answer in, and Achieve did not like it. And that makes you think, oh, you've done something wrong. No, you have not if you've done it this way. This is a correct answer. But what Achieve is wanting you to do here in order to make this, I'll say, a slightly better answer, is after you integrate, they're wanting you to use the double angle identity. And that the fact that the sine of 2u is equal to 2 sine u cosine u. So that you should have learned at some point in trigonometry. We're going to have to know it now in some of our integration problems. So when this sine 2u is up there, I said, well, that's just 2 sine u cosine u. The 2 here would cancel with the 2 in the denominator, and you'll see that's why it's back to just a 1/10 as its coefficient. And then I would have the sine of u times the cosine of u. Well, the sine of u becomes the sine of the group sine of 5t. And then I would have times the cosine of u. Well, the cosine of u, the cosine of that angle, the sine of 5t. That's a lot of parentheses. The cosine of, the sine of 5t, close, close. So please make sure you use your parentheses correctly in this problem, plus your constant integration. And then once you get that answer, Achieve is happy with it. But I do want to reiterate, in order to get to the answer that they expect here, you're going to have to use that. Oh, wait a minute. This is another one of those that I alerted the Achieve staff of and let them know that I had the correct answer previously. So you can take back my warning. You can put this answer or this answer. Initially, Achieve did not accept this answer for me. But after I fussed at them, I guess, and their tech support, they're accepting it now. Yeah, you can see that they accepted mine. But the first time I entered that answer in, they did not, and I thought I had to put the other answer. So it's working now as far as that goes. Whenever we go to look at our next problem here, number 16. So keep in mind here, this answer using the sine of 2u and plugging that in, that will work. Or if you use the double angle identity to simplify it further, that'll work too. So either one. Next problem, short problem. Don't you hate short problems? But the good thing about this one is that it does use the power reduction formula again, this time for the sine function. So I went ahead and showed it down here with the arbitrary angle A. I wanted to remind you of something that you learned in trig that says the sine squared of the angle A is equal to 1/2 times the group 1 minus the cosine of twice the angle. The power reduction formulas for the cosine squared and the sine squared, they look identical, and they are identical, other than the cosine squared is always plus the cosine of twice the angle, whereas the sine squared is minus the cosine of twice the angle. All right, so now when I'm looking at this problem, that's the integrating from 0 to 19 pi over 2 of sine squared of 13x, I say, I can't do that because it's a power of a sine function. Use the power reduction formula. I brought the 1/2 out in front, and then on the inside, it's going to be 1 minus the cosine of twice that angle, so the angle becomes 26x. Now I can integrate that with respect to x. Notice I didn't even need to use substitution here. The integral of 1 is x. The integral of the cosine of 26x, that's going to become the sine of 26x. So I have, since this was a minus, this is still a minus. The sine of 26x divided by the derivative of that angle divided by 26. We're now evaluating this from 0 to 19 pi over 2. When I plug the 19 pi over 2 in, of course, the first term is 19 pi over 2. Your second term, you're taking 26 times 19 pi over 2. The 26 and 2 would reduce down. This is just 13 times 19 pi. And you say, well, okay, that's going to be number of pi revolutions. At every multiple of pi, the sign is 0. So you say, oh, that's where you got the 0 from there. And then the same thing happens when you evaluate at the lower limit. Both the first and second term are 0, since the sign of 0 is 0, and since 0 is 0, the bottom limit doesn't give me anything. So this ended up just being, and I forgot to put the final answer there, 1/2 times 19 pi over 2, and we know that that is 19 pi over 4, and this pen is not writing very well. 19 pi over 4 for my final answer there. Again, that's the only way to do that problem is if you understood to use the trig identities in the first step of it. All right, now number 17. We have the integral of sine to the 5th x from pi over 3 to negative pi over 2. Okay, as soon as I see an odd power of a trig function, well, particularly a sine function, I know I'm going to write all but one power of it in terms of cosine. So sine to the 4th is the same thing as the sine to the 2nd squared. Sine to the 2nd is 1 minus cosine squared, quantity squared. And then I can say, all right, let's do a u substitution. Let u equal cosine. Derivative of cosine is the negative of the sine with respect to x. I didn't see the negative in the problem, so I multiplied the inside by -1, multiplied the outside by -1. And then I also changed my limits of integration. I said, well, your lower limit, it was in terms of x. In terms of u, it's going to be u is equal to the cosine of pi over 3. Cosine evaluated at pi over 3, that's 2/3 of the way through the first quadrant. It's going to be 1/2 at that point. You know that the cosine at pi over 2, that's straight down on the unit circle. At that value straight down, the x component is 0. That's where I'm getting the 0 there. So we're integrating from 1/2 up to 0. And then all I've done in this step is said, well, this is going to end up being 1 minus u squared. 1 minus u squared quantity squared gives me this polynomial. Once I get to that, it's just power rule. First term integrates to u, second term integrates to 2u cubed over 3, the third term u to the 5th over 5. You evaluate that from 1/2 to 0. At 0, clearly we get a 0. The only answer we get is when we evaluate it at 1/2, so I would have said I need to subtract the lower limit, but then when I subtract the negative out in front, then I will be adding. When I evaluate this at 1/2, I got 1/2 times 2/3 times 1/8 gave me 1/12, so minus 1/12, and then the last term would have been 1 over 32 divided by 5, which is 1 over 160. For that, I combined those to get 203 over 48, and Achieve does want a nice exact answer there, so it needs to be that one right there. Now, for this next one here, and I forgot to circle my answer for it, we have the integral from 0 to pi over 4 of 19 over the cosine of x integrated with respect to x. Now, this is one of those that really don't have a lot of techniques to do with it. I went ahead and factored the 19 out and said, well, 1 over cosine, that is the secant function. And you might remember, we didn't really ever say the secant as an answer in Calc 1 when we thought of our derivatives. We know that the derivative of secant is secant tangent, but we didn't say the derivative of blank is the secant function because it's not a straightforward problem in that sense. Now, there are ways to work that out, and I think I showed that in the notes in an earlier section, but typically whenever we get to these, we're wanting you just to go in and use your table formulas. The table formulas, I've put them on your Brightspace page underneath where I've done the section videos, the lecture notes for each section. You'll notice I have this posted in there. It's also in the back of your book. So in this case, you'll see I use table formula number 13. It's the secant formula right there. The integral of the secant of u du is the natural log of secant u plus tangent u plus the constant of integration. So that enables me to go in and now work my problem and say, well, all right, he said it was just the natural log of the secant of that angle plus the tangent of that angle, or he didn't say it, but formula number 13 on the table. Now, whenever you're using good notation, if you want to show the reader that you're using a table formula, then you just do it like that right there. So over the equal sign, I put number 13, meaning I've used the table to integrate from here to here. And now I'm evaluating this expression from 0 to pi over 4. So I'm thinking, okay, it's the secant of pi over 4. I know in my head, well, the cosine of pi over 4 is the square root of 2 over 2. So the secant of pi over 4 is the reciprocal of that. It's 2 divided by the root of 2. Well, 2 divided by the root of 2 is the root of 2, because 2 is the same thing as the square root of 2 times the square root of 2. You're canceling one of those out to get the root of 2. So the secant of pi over 4 is the root of 2. The tangent of pi over 4, it's just saying, well, we know that the tangent of pi over 4 is 1 because it's the ratio of the sine over the cosine, and they're the same value there. So I get those when I evaluate at the upper limit. Now minus the lower limit. It'd be the secant of pi over 4. Sorry, the secant of 0. And you say, well, the secant of 0, we know that the cosine of 0 is 1. Secant's the reciprocal of that, so it's still 1. But then you'd say plus the tangent of 0. Tangent of 0 is 0. So I just get the natural log of 1, and then you might recall, or hopefully you do recall, instead of you might recall, I hope you recall that the natural log of 1 is just 0, so I can ignore that, and then I'll just have 19 natural log of the absolute value, and don't even need the absolute value since that's positive anyway, of the root of 2 plus 1. Excuse me. Now, something I do want to remind you here, I was saying you don't need the absolute value, and in fact, you shouldn't put it. I think if you try to put an absolute value around this one, Achieve will count it wrong. It really shouldn't count it wrong, but it does. So 19 natural log of, remember, just the group, the square root of 2 plus 1. No natural log needed there. Last two problems in this section, you'll see neither one of them was too bad. We have the integral from negative pi over 52 to pi over 52 of the secant to the 4th power of 13x integrated with respect to x. So the first thing I did here in this problem is I said, okay, I have an even function. When you think, ooh, even function, well, it's a 4th degree function. Every single even function in existence is going to be symmetric with respect to the y-axis. So I can say, well, whatever happens from negative pi over 52 to 0 is going to be a mirror image of what happens from 0 to pi over 52. So instead of integrating from negative pi over 52 to pi over 52, I just decided I'm going to integrate from 0 to pi over 52 and take that answer, multiply it by 2. That's going to be the answer to the entire region and make it a little bit easier to evaluate. Okay, so now, once I did that, then on the inside, anytime you have an even power of secant, you break all but 2 powers of it down into the tangent function. You say, well, I know 1 plus tangent squared is equal to secant squared. So that's my first secant squared. The other secant squared stays here with the dx. Now I'm going to let u equal the tangent of 13x. We know that the derivative, and the reason you leave 2 powers of that secant there is because the derivative of tangent is secant squared of 13x times 13 with respect to x. So I know that this substitution can be done beautifully if I see a factor of 13 in there. I didn't have it in there. Well, I multiplied by 13 on the inside, which is why I divided by 13 on the outside. Now, on the outside, I'm going to have a factor of 2/13, and it'll be now the integral from 0 to 1. Why did my limits of integration change? Because I'm changing everything on the inside into terms of u. So my limits now in terms of u, I had to say, well, u evaluated at the lower limit would be the tangent of 0, 0. U evaluated at the upper limit would be the tangent of 13 pi over 52. 13 pi over 52 is the same thing as pi over 4. The tangent of pi over 4, 1. So now instead of integrating from 0 to pi over 52, I'm integrating from 0 to 1. The inside is going to be your 1 plus tangent squared becomes u squared. And then please remember, everything else became du. That makes it super easy, guys. The inside's just u plus u cubed over 3. We get that. Integrate it, or sorry, evaluate it from 0 to 1. When you evaluate this at 1, the inside's going to be 4/3. When you evaluate it at 0, it's just 0. So you get 2/13 times 4/3 for a final answer of 8/39. The last one here for number 20. Again, a pretty quick problem. We have the tangent of 8x integrated with respect to x from 0 to pi over 24. So as soon as I saw the tangent in there, I was thinking, okay, I'm going to need to put this in terms of sines and cosines and then use substitution. So I got it as the sine of 8x over the cosine of 8x. If I enable u to equal the denominator, the cosine of 8x, I know that the derivative of cosine is negative sine of 8x times 8 with respect to x. So I get negative 8 sine of 8x dx. I didn't have the factor of negative 8 on the inside, so I multiplied the inside by negative 8, and then I had to negate that by dividing by negative 8 on the outside. And so now this just makes up for this, but on the inside, that negative 8 sine of 8x dx, all of that's going to become du in this step. So the only thing I have left in there is going to be 1 over the cosine, which is 1 over u. My outside negative 1/8, I went ahead and changed my limits of integration, or I had to, because now it's in terms of u. U evaluated at the lower limit would be the cosine of 0, which is 1. U evaluated at the upper limit, you're plugging a pi over 24 into that, you get 8 pi over 24, which is the same thing as pi over 3. So it's asking you, what is the cosine function at pi over 3 radians? It's 1/2. It's still an x component on the unit circle of 1/2. So I'm integrating from 1 to 1/2 of the integral of 1 over u du. I know that's just going to be the natural log of the absolute value of u. The absolute value is not necessary in this problem since both limits are positive anyway. So I'm evaluating the natural log from 1 to 1 over 2. My upper limit's going to be the natural log of 1 over 2. My bottom limit's going to be the natural log of 1, which is 0. So I can ignore that bottom limit and just say, well, this is going to be negative 1 over 8, the natural log of 1/2. Now, you could have left your answer like that. I tried to be a little neat with it and say, I don't like that negative out front. Any negative out front can go up as a negative exponent. And think about if you raise 1/2 to the negative 1 power, that makes it 2 over 1. It makes it take the reciprocal of what's on the inside. So I just thought 1/8 natural log of 2 looked like a cleaner answer here. But whether you put the negative 1/8 natural log of 1 over 2 or the answer that I have that I think is better, both would have been correct on Achieve. And you can see that it liked that entire section there of answers. So hopefully you have as much fun with this section as I did. The next section, 7.3, that's dealing with trig substitution, while they are gorgeously fun problems, getting to the answer that Achieve wants in the next section can be tedious sometimes. And I think you'll see what I mean when we get into some of the problems in that section. So they're not quite as fun as these problems, but they're still extremely important and good problems that need to be looked at. So hopefully you're good with this section, but let me know if you have any questions, and look forward to the next section, which is trig substitution. So we're going to take problems that have no trig in them and make them all trig stuff. It's gorgeous.